So part of our curriculum is to get into section 7.3. I'm not going to go deeply into this section. I'm just going to scratch the surface. We want to introduce what subgroups are. So what is a subgroup of a group? So the idea is you have a group G. So that's a non-empty set with some operation we call star that satisfies 4 axioms. So a subset H of a group G is a subgroup of G, provided H is itself a group under star. So the idea is you have this set H here inside of G, and it is itself acting as a group under the same operation. So it's basically a group within a group, and they have the same operation. So here's some facts, probably worth mentioning. G is a subgroup of itself. So G is a subgroup of G, right? G is a group inside of G. That's kind of stupid, but it's true. Another famous group is the set containing just the identity element. This is a subgroup of G. So why is the set containing the identity a subgroup of G? Well, first of all, it's a non-empty set, right? It's contained in G. It's closed under the star operation. So if I took the identity times the identity, I get the identity. That's the only element. It has the identity. All right, it has associativity. And it has inverses, right? E inverses E. So it has the 4 axioms. This is sometimes called a trivial subgroup of G. Called the trivial subgroup of G. So that's the name that we give just the identity element inside of a set. It's called the trivial subgroup. And so here's some terminology. All subgroups of G, besides G itself, are called proper subgroups of G. So a proper subgroup is just a subgroup of G that's not G itself. So I want to draw some what are called lattice diagrams of subgroups. So a lattice is a diagram, basically, that shows you kind of how subgroups are, how subgroups are subgroups of other groups. Yeah. Okay. Lattice of additive subgroups of the real quaternions. Remember, the real quaternions is represented by H. So I'm going to start with the real quaternions. So our operation here is addition. So the identity would be the 0 element. Would be the identity here. Now think about what these are. These are what? The set of all A plus BI plus CJ plus DK. A, B, C, D are real numbers. I squared equals J squared equals k squared equals -1. I times j equals k. J times I equals -k. How does it go? I, j, k. So I times j is k, j times I is -k. K times I is j, I times k is -j. What else? K times j is -I. Have I done that? And j times k is I. I haven't done that. J times k is I. Okay, that's the quaternions. So I'm going to draw a bar here. So this bar means what's under here is a subgroup. So the next group here would be the complex numbers. So the complex numbers are a subgroup of the quaternions. And what are the complex numbers? It's the set of all a plus ib, such that a and b are real numbers, and I squared equals -1. Yep. So then beneath this, so these are additive groups here. Then we got the real numbers. And then a subgroup of the real numbers would be the rational numbers, right? Fractions. So fractions are always contained in the real numbers. And then what else do we have? We have like integers, right? Integers are contained within the rationals. Then we could do something like within integers, there are even integers, 2z, right? These are even integers. And you can do like 4z. You could do like 8z. I'm just going to say, okay, down here, I'm going to have the trivial subgroup, which would be the set containing just 0. So these are all additive groups, groups under addition. It turns out they're all abelian. So addition commutes here. These elements commute under addition. So we have this is called a lattice. This diagram is called a lattice. So you got your top group at the top is the real quaternions, then a subgroup, complex numbers, then a subgroup, the real numbers, subgroup, and so on, all the way down to the smallest subgroup would be just the trivial subgroup, which is the set containing 0. So these are a lattice of additive subgroups. Let me do a lattice of multiplicative subgroups of H star. Lattice of multiplicative subgroups of H star. Now what is H star? It's the real quaternions, and basically you're just throwing away the 0 element. So that turns out to be a group under multiplication. It's not abelian because multiplication does not commute, but every non-zero element does have a multiplicative inverse. So I'm going to start with H star at the top. It's going to be my large multiplicative group. So take the real quaternions and throw away the 0 element. All right. And then over here, take the complex numbers and throw away the 0 element. Now the complex numbers, you throw away the 0 element, you're going to have a group under multiplication. Why? Because every element has an inverse except the 0 element. And actually, this one is abelian. C star is abelian. So while H star was not abelian because multiplication does not commute in H star, C star is abelian because multiplication, the elements commute with regard to multiplication. Oops. Don't know what that's about. Okay, so what else am I going to do? I'm going to do R star. So R star, you take the real numbers and you throw away the 0 element. So you got positive numbers, negative numbers. We're talking about decimals, including pi, including e, including like the square root of 2. So this is going to be a group under multiplication. It's going to be abelian because multiplication commutes here. Okay, underneath R star, I'm going to write R plus. So these are just the positive real numbers. So the positive real numbers are contained within the non-zero real numbers. And you think about it, that's going to be a group under multiplication. A positive times a positive is a positive, right? So you got closure. You have the identity as 1. The multiplicative identity is 1. You have inverses, right? If I have a positive number, it's going to have inverse. So for example, the number r that's positive is going to have 1 over r as the multiplicative inverse. It has associativity. So under that, a subgroup of that you could say is the rationals plus. So the positive rationals. Positive rationals are contained within the positive reals. And you can keep going. You can't put the integers plus, right? If you put the integers, they don't have inverses necessarily. So what I'm going to do, I'm just going to put here, I'll just stop and I'll put 1, the set containing 1 here. That's a trivial subgroup here, the trivial subgroup. Okay, the trivial subgroup, the set containing just the identity element. It turns out, though, that actually R star, what's R star? Those are the positive and the negative real numbers. We threw away the 0 element. There's a subgroup 1, negative 1. Just 2 elements. Right, that's a subgroup, right? It's closed under multiplication. 1 times negative 1 is negative 1. 1 times 1 is 1. Negative 1 times negative 1 is 1. Yeah, and it has the inverses in there, right? The inverse of 1 is 1. The inverse of negative 1 is negative 1. It has associativity, yeah. And it turns out that the set containing the identity, the trivial subgroup, is a subgroup of that. Now going to the complex, I can do the complex numbers here. The complex numbers have a subgroup plus or minus 1. So let me list it out in detail. 1, negative 1, I, and negative I. That's a subgroup of the complex numbers. And it turns out that 1, negative 1 is a subgroup of that set of 4 elements. And also the real quaternions star, that's the real quaternions, get rid of the 0 element, has a subgroup, a finite subgroup, called the quaternions. So you got 1, negative 1, I, negative I, J, negative J, K, negative K. Now these guys are a subgroup of H star, and it turns out 1, negative 1, I, negative I are a subgroup of the quaternions there. So this is a lattice of subgroups here. Now these are all multiplicative. Let's do an example here. I want to do a lattice of multiplicative subgroups of U12. lattice of multiplicative subgroups of U12. You think about U12, these are what the units of Z12. You can list those out. 1 bar, not 2 bar because 2 bar is not relatively prime to 12, not 3 bar, not 4 bar, 5 bar, 6 bar is not relatively prime to 12, 7 bar, not 8 bar, not 9 bar, not 10 bar, 11 bar. Okay, so U12, these are the units of Z12. This is a multiplicative group. Here's a subgroup. One bar and 11 bar. So that set of 2 elements. So you think about it. If I take 1 bar times 11 bar, that's going to give me 11 bar. So 1 bar times 1 bar is 1 bar. 11 bar times 11 bar. That gives me 121 bar, but that reduces modulo 12 to 1 bar. So we have the closure. We're going to have inverses. 11 bar is going to be its own inverse, because when you multiply 11 bar by 11 bar, you get 1 bar. Okay, so that's going to be a subgroup. Here's another one. 1 bar and 5 bar. It's going to have closure. 1 bar times 5 bar is 5 bar. 1 bar times 1 bar is 1 bar. 5 bar times 5 bar is 25 bar, which when you reduce it modulo 12 is going to be 1 bar. So it's closed. 5 bars is going to be its own inverse. Yeah. Has an identity, 1 bar. And there's another one here. Another subgroup of U12. It's a 2-element subgroup. 1 bar, 7 bar. It's going to be closed. 1 times 7 is 7 bar. 7 bars times 7 bars. 49, but reduce that modulo 12, and you're going to get 1 bar. Yeah. 7 bar is its own inverse. 1 is its own inverse. It has the identity 1. And then these 3 subgroups are all going to have a common subgroup, just the identity element, 1 bar. 1 bar. Okay. Now there's a lattice for multiplicative subgroups of U12. Okay, do I want to do anything else? I think I'm going to stop there. So in our next video, we're going to do something called the 2-step subgroup test. We're going to talk